So within the laboratory, a big cohort of patients that we look after and provide diagnostic testing for is children that are referred to us from clinicians to try and find the cause of their developmental delay and intellectual disability. And as a cohort, this group of patients sit within the rare diseases group. And it's been well reported over the last few years that individuals with undiagnosed rare diseases, including these children, can sometimes face a years-long diagnostic odyssey that sees them going through the healthcare system looking for a diagnosis with multiple appointments, investigations. It really can take such a long time for them. But there's been such an explosion in new genomic technologies in the last few years that they've got the potential to have a real impact on speeding up the time it takes for these families to receive a diagnosis. And again, for the patients and for the healthcare system as a whole, there's real potential to avoid unnecessary investigations. And in some cases direct patients to the right treatment earlier on as well. So it really has got the potential to have a big impact. Recent figures from NHSE have estimated that the cost of this diagnostic odyssey is between £35,000 and £1 million per child by the time they reach 5 years old. That's just for one child. And that's to say nothing of the impact on the quality of life and the experience over this journey that can last years and years and years for the families and those patients as well. So therefore, genomic medicine has the potential to save costs and improve the quality of care by targeting patients to the right treatment, maximising the benefit for them and reducing side effects and reducing harm. So the project that I've been working through is looking at one of these new proposed technologies to see how this might fit into that pathway and how it might have benefits to patients. There's lots of different ways we can utilise these technologies, and this is just one potential avenue that might bring benefit. So by new genetic technologies, the difference this is made, and one of the more significant ones is next generation sequencing. And the real advantage of this next generation sequencing is that rather than testing one gene at a time in a really stepwise manner, you test one gene. If you get a diagnosis, that's fine. If you don't get a diagnosis, you test the next gene, then you go on to the next gene. You can really start to imagine how this diagnostic odyssey that lasts years and years and years builds up as you have to test one gene at a time, bearing in mind there's 20,000 genes in that order in the human genome. So you can really see why that takes such a long, you've got a huge pool to fish in to try and find the gene that's going to cause a diagnosis. But these new next generation sequencing technologies, of which there are various forms, mean that you can test lots and lots and lots and lots of those genes at the same time. So in one test, you can get the same amount of information as where it would have previously taken you years to get that. So it's really revolutionising the pathway for these patients. So what we're hoping with the technology that we've been evaluating with our technology partner is that the new test that they've implemented or that they developed can combine elements of one test that we do and elements of test 2 that we do, and we can do them at the same time for there and around the same cost of our current testing pathway, thereby reducing the diagnostic time for a subset and a cohort of patients, and that we could potentially, for those patients, reduce the journey from years to months, which is really significant. As an example of this, and this case study is not unusual, I would say this is fairly typical of testing going back even just a year or two. We had a patient from a 3-year-old child with a variety of clinical features, including developmental delay and other features such as speech delay, some hearing loss, some dysmorphism. And this here is just a list of all the tests that this child had to go through and the time scale that it went through until she eventually found her diagnosis in 2016. So if you notice that the child was 3 when she was referred, this journey and all of these tests, irrespective of the cost, took 7 years. She was 10 by the time she achieved a diagnosis. You can really see why it's so critical to use the technologies as best as we can to get that diagnosis as early as possible for the patients. So the tests that I really want to focus on in talking about this project are the 2 tests at the bottom. So the ones that's called ARRAY-CGH and trio-based clinical exome sequencing. So these 2 tests, I would say, are the 2 most common, most fundamental tests that we use in the testing pathway for patients with developmental delay and intellectual disability. So ARRAYS looks for one kind of genetic cause, and clinical exome sequencing will look for a different type of genetic cause. So this project that we were running was to investigate a new test that could potentially do the array CGH test and the clinical exome sequencing test in one test. We were really getting two, like for the price and in the time scale of one, and using one set of equipment rather than two separate pieces of equipment. So it really did give us an opportunity for patient benefit and efficiency within the laboratory as well. So the aims of this project were to work with our industry partner to assess their new test and assess this test against our current practice. And we were going to assess the impact of this technology against our current key performance indicators. So the aims were to perform a technology assessment of this new test to make sure that the laboratory workflow and the efficiencies meant that it was quicker, that there was less staff time needed, that there was less equipment needed, there was more efficiency in the system. We needed to do a technology assessment of the performance of the new test. So is it robust? Is it reliable? Does it fail more frequently than our current test? Does it pass more frequently than our current test? What's the repeat rate? What's the failure rate? And then importantly, we need to look at the diagnostic detection rate. So does this test perform as well as both of our current separate tests? Because that's really key. This needs to be better than what we're doing currently rather than the same or worse. So they were the three things that we wanted to test in this proof of principle project. So against the first aim, we were able to successfully process a number of samples in the laboratory. The staff that were doing the technical work had really positive feedback about the ease of the testing and the protocol and the efficiency. Bearing in mind that to get the same results as this one test, we would have had to process two tests previously. Again, it represented an additional time saving. And again, because we were doing one test instead of two separate tests, like I've kind of said before, that meant we only needed one set of equipment rather than two. So we were able to show against the first aim that there were real efficiencies to be gained by implementing this test. Against the second aim, what is the performance of this test? How robust is it? How often will we get the result we want for the patient? I think we need to do some more work to look at this here. There were a small number of failures. However, as it was a brand new protocol within the laboratory, we couldn't rule out that this was just people getting used to the technology and to the protocol rather than actually anything to do with the kit. So I think we need to run a few more kits now that we're used to it within the laboratory. And then the third thing that we needed to look at was, does this new test give us as good or improved diagnostic rates compared with our previous test? So to do this, we reran a number of genetic aberrations we'd previously detected using other technologies and made sure that we could detect them using this platform. And in all cases, we were able to detect the previously detected variants. So it looked like this platform had real potential to give the equivalent diagnostic performance as our previous tests. So it was a proof of concept test. It established to us that there was utility in proceeding to a full evaluation of this test. So there is future work that we need to do to work up to the point where we can say that we would want to implement it into clinical service. But as proof of concept, it certainly showed that there was the potential there to have big efficiencies and benefits in the laboratory. The things that we really want to look at in future with regards to this platform prior to any clinical implementation are to do a further technical evaluation and optimization. Because this was proof of concept, we deliberately picked like the good quality samples that we knew would work. It wasn't necessarily reflective of a real life situation. So we'd almost need to run in parallel to make sure that we weren't pre-selecting the good samples to make sure it really was robust in real life. We'd want to do a pilot study of live cases. So again, we tested on cases where we knew the result. We'd want to run them side by side on cases with an unknown result and make sure that we got equivalent results. And what's really going to be quite important, I think, is going to be a cost analysis of using the proposed new test. Because although we have the cost of the reagents, which is relatively simple to do, in terms of trying to describe the value of what this could mean overall in terms of staff time, equipment efficiencies, patient getting that diagnosis earlier on is quite a complex model to try and work out against the diagnostic yield. So I think that's quite a big piece of work, but I think that will be the next key to this pathway in terms of us deciding how proceedable this option is. So that's our future scope of work towards moving this from proof of concept into deciding if we proceed with a full clinical implementation. I think that was the end of my presentation. So thank you to our partners who supported us and to the lab team. We've done a lot of work on this project. So thank you, everyone.